This question asks, how many diastereomers will the following molecule have? So in order to be able to answer this question, we need to know what a diastereomer is. Diastereomers are kind of a catch-all category for molecules that are related to each other by being stereoisomers, but they are not mirror images of each other. So they have to have the same molecular formula, the same connectivity, and they aren't mirror images of one another. Certain diastereomers that you may have heard about before are cis and trans diastereomers, or molecules that have two or more chiral centers can also have diastereomers. So let's take a look at the example that we have on this slide. This is a molecule that has two chiral centers. So those two chiral centers are chiral because they have 4 unique groups attached. Note the hydrogen atoms aren't drawn in, but they're there. And so we can think about the 2 to the n rule here to kind of predict the maximum number of total stereoisomers that this would have, including this one. So this would be a 2 to the 2, which is 4. And we can go ahead and draw these molecules out. Okay, so we have molecule number 1 already provided for us. We can think about this molecule's enantiomer. This molecule's enantiomer would look like this, where we've changed the absolute configuration of those 2 chirals, and they're now going to both show up as being both dashed. That's molecule number 2. In theory, we could have molecule number 3, where instead of 2 dashes, we now have a dash and a wedge. Oops, I'm going to draw that wedge better. Dash and a wedge. And then a 4th molecule. So it looks like this, where it goes wedge and then dash. All right, so this is our max for number of stereoisomers that are possible. Anytime that you have 2 chiral centers or more, you always have to have a little red flag go off in your mind that asks you to think about symmetry as well. So a molecule that has 2 or more chiral centers and a plane of symmetry is a special type of molecule called a mesocompound. Mesocompounds are important because they are identical to their mirror image. And so if you have a mesocompound present amongst the different possible stereoisomers, that's going to make it so that you have fewer number of stereoisomers than predicted. So let's take a look at our molecules. Molecule 1 has no symmetry. We're mostly looking for planes of symmetry in these examples. Molecule 2 also has no symmetry. We can also kind of prove that to ourselves. If we want to, we could rotate this single bond between those 2 chiral centers and think about what these molecules might look like if the 2 ethyl groups are going to be on the same face as each other. When we rotate that bond, one of the dashed methyls becomes wedged. Okay, so again, you can see that there's no symmetry in this molecule either. If we do the same analysis for molecule 1, we end up with a wedge and a dash. So again, no symmetry in either form. It's important to remember to rotate single bonds because sometimes a molecule might look like it doesn't have symmetry, but if you rotate the single bond, then the symmetry will become apparent. So let's look at molecule number 3, for example. In its current form, it doesn't really look like it has any symmetry. But if we rotate that bond, we will find that we have 2 dashed methyls on either side because the wedge rotates around and goes back. So this is a molecule that has symmetry, but it's very kind of sneaky because we didn't notice it in the way that the original molecule is drawn. If we do the same analysis for molecule 4, what we find is, again, a molecule that has symmetry. So what does this mean for molecules 3 and 4? It means that these 2 molecules, 3 and 4, are the same, or they're identical to each other. They are not molecules that will have enantiomers, and they're not unique structures because of their symmetry. So they're superimposable with one another and therefore identical to each other. So let's next think about the relationships of these different molecules to our original. So our original is up here, drawn in for us. Molecule number 2, as we mentioned, is the enantiomer of that molecule. Because that molecule does not have symmetry, it can have an enantiomer. So this molecule has 1 enantiomer. And because molecules 3 and 4 are identical to each other, they will only have 1 diastereomer as well. Okay, so it's not two separate diastereomers because molecules 3 and 4 are identical to each other. So if we want to go back and answer our original question, how many diastereomers will the following molecule have? It's going to be one, only one diastereomer, because the diastereomer is a meso compound with a plane of symmetry.